I'm Abdel. I'm working at Starkware. So basically, Starkware, we are building zero-knowledge proof technology, and we use zero-knowledge proofs to build basically scalability solutions. And today, I'm going to talk about the potential use cases of zero-knowledge proofs, and specifically Starks, to potentially improve Cashu on some aspects. So, namely, potentially reducing the trust assumptions on the mint, improving the overall security of the protocol, while maintaining privacy features, because obviously it's the core nature and goal of Cashu. So we don't want to break those privacy aspects of Cashu, of course. So TLDR of Cashu, just to put the basics to explain how to use zero-knowledge proofs. You have users that can send or receive ecash tokens. Then you have the mint, which is a server, the operator. The core part of Cashu is based on elliptic curve cryptography, and specifically the core of the scheme is called the blind Diffie-Hellman key exchange, or BDHKE. So for the flow, users want to mint some ecash, so they request a Lightning invoice and pay it. They generate a secret, they blind it with the blind Diffie-Hellman key exchange protocol. They send it to the mint signs it and returns the blind signature, and then the user can unblind it and get ecash token. Then it can do whatever he wants with the ecash token, for example, sending to someone else, and then the person that wants to get some sats in return to those tokens, they can send the token to the mint, and the mint will check basically that the signature is correct. And if the secret has not been seen before, then it means that it has not spent yet, and then it can burn the token and pays the collateral over Lightning. Okay, then now there are some limitations on Cashu. The first one is obviously the high trust requirements on the mint that can do a rug pull, basically steal assets of all users, or potentially just shut down and become unresponsive and censor all transactions, this kind of stuff. There is some kind of lack of transparency on the reserves of the mint. And there is limited offline protection, because if you are not connected, you cannot have like full protection over double spending. You need to interact with the mint to have good protection against double spending. Now there is potentially a way to combine the proof of liability scheme that Kali designed and using Stark proofs to improve those aspects. Okay, so I will try to give a general overview of Starks. So Starks means scalable, transparent arguments of knowledge. So it's a kind of zero-knowledge proofs that have some interesting properties. First of all, scalability. Why? Because the proving time is quasi-linear. So what does it mean? It means that it's exponentially faster to verify the proof compared to re-executing naively the computation. So usually in blockchain, on Bitcoin, the way you make sure that the system is acting honestly is by having full nodes that run the computation naively. Everyone is running the same computation. But of course, it's a problem, because if you don't want to hurt the decentralization of the network, you cannot put more hardware requirements on the node. So you have to choose. And of course, decentralization and security is the main important aspect of Bitcoin, so we cannot sacrifice that. But with zero-knowledge proofs, you don't have to choose, because you can break this asymmetry of power, and it's exponentially faster to verify the proof, even with a small device. Even if the prover has 1 million times more power than you will still be able to verify the proof very quick and cheap. Starks, there is the transparency in the sense that there is no trusted setup. So the trusted setup is basically a ceremony where there will be some participants that will contribute to generating some randomness, basically, and the system will be secure if there is one honest participant. You can consider that it's fine, but in fact it's not, because of course if the ceremony is open and permissionless and everyone can participate, you have the chance to participate, and if you do it correctly, you know that the system is secure. But like in 10 years, maybe people won't have the chance to participate in the ceremony, so they will have to rely on the fact that 10 years ago, people did the ceremony correctly. So you don't want that. So Starks are very good for that because they are transparent. There is no trusted setup. They are post-quantum secure because they are purely hash-based. The Starks are not using some fancy elliptic curve pairing operations. Most of the like snark systems and so on, they are using elliptic curve pairing operations, which are not quantum resistant. So Starks are quantum secure. So it's good to build a system that is future-proof and that will be valid even when quantum computers become a threat. And then they are succinct because the proof is small and quick to verify. And the good thing is that the proof size is linear. So it does not matter how much computation it represents, it will be always the same. So that's why it's also, the more you batch computation, the more interesting it is because the proof size is always the same. And it's super quick to verify it. Now let's talk a bit about the proof of liability scheme. So I invite you to check the link with the whole description of the protocol designed by Kali. But the TLDR is that there is this idea of mint and burn reports. There is a notion of key set rotation and epochs. So the idea is that you will split and maybe have epochs that will last a month or something like that. And after each epoch, the mint will do a key set rotation. And for an extended period of time, the mint will still accept, of course, all tokens, but that after some point, not. And then you have this notion of user verifying that the mint is not cheating. So how does it work? The mint publishes a list of all the issued tokens. So this is the mint proofs. And then you have the mint that publish also the list of the burnt tokens, the redeemed tokens, basically. So this would look like this. And then you can know the outstanding balance of the mint, depending on that. And how you detect cheating mints, so it's relatively easy for users. Like, because if the mint is artificially minting some unbacked ecash, users can prove that their tokens are not present in the mint proof, so that means that the mint is cheating. But there is a caveat here because they will have to dox their ecash, so it's not good for privacy. But it's easy to detect that the mint is cheating, which is already an improvement. And then if the mint is inflating the burn proof list, because it can just generate some ecash and pretend to burn them, users can contest if basically their unspent tokens exceed the reported balance of the mint. But for that, you will need some kind of synchronization of users if they want to prove that the mint is cheating. So now the idea could be to combine Stark proofs with this proof of liability schemes to improve both the security and also the efficiency. So the idea will be the mint, instead of just publishing naively the reports, it would generate a Stark proof of the correctness of the reports in addition to the data. So yes, those proofs will be included in the published reports. It can be on Noster or whatever way of publishing the reports. And then users, they can efficiently verify the integrity, and they would not have to download all data because they can just verify the correctness of the reports by verifying the Stark proof. And also a good aspect is that they could be able to generate a proof that the mint is cheating without doxing their ecash. So it's good for privacy. Now, if we want to go even further, so this is an hypothetical scenario in the sense that it would require a soft fork on Bitcoin. So we don't know if it will happen, but yes, let's try to think about this scenario. So in this scenario, the idea would be to be able to verify the Stark proof on chain on Bitcoin. So it happens that all we need for that is opcat. So I guess everyone knows, but opcat is simply an opcode that takes two elements from the stack and concatenate them and push the result back on the stack. So it was present in the early days of Bitcoin. It has been removed in 2010 by Satoshi with a bunch of other opcodes. because there was some bug in the implementation. There was no control check on the resulting size of the stack. So it could be a DOS vector that could lead to potentially being able to shut down the full nodes. So of course, it was good to remove it, to disable it at this time. So yeah, as I said, it happens that they enable the construction of a stock verifier on Bitcoin, and it's surprising, right? Because this opcat is literally 9 lines of code, and it just does concatenating two elements on the stack. So it's surprising that it could enable something as complex as a stock verifier on Bitcoin, and I will try to give you an intuition on why. And it's not just a theory. We implemented this stock verifier in Bitcoin script using opcat, and we demonstrated it on a Bitcoin signet. So I will put the links in the presentation with all the transactions on Bitcoin signet. So yeah, it works. We actually, with opcat, we can implement a stock verifier in Bitcoin script. So how come? So opcat is actually perfect for Merkle tree verification, and the Star protocol involves a lot of Merkle tree verification. There is a bunch of Merkle tree verification that you need to do, and opcat is very good for that, of course, because the whole point of a Merkle tree is to take two elements, to concatenate them, to hash them. So this is literally why opcat is perfect for Merkle tree verification. Then I forgot to mention, but with star proofs and zero knowledge proofs in general, this is not binary arithmetic. Everything is modular arithmetic. So we are working with polynomial, basically. And it happens that the field that we are using on our new prover is perfect for Bitcoin because it's called Mersenne M31. So it's a 31 bits prime field, and it works super well with the 4 bytes arithmetic of Bitcoin script. So it's a very good match. And then not only you need the ability to verify the star proofs, but if you want to be able to maintain a logic on the Bitcoin script on Bitcoin, you need covenant. You cannot do that without covenant because anyone that can spend the transaction could change the logic. So you don't want that, of course. You want the ability to be able to maintain the logic of the smart contract or the script. And it happens that if you combine opcat with opchecksig, it gives us covenants. So there is the catch-nor trick that is described by Andrew Polstra. He did one article explaining exactly how this trick works. But TLDR is that the combination of those two opcodes give us covenants, and then with covenants, we have the ability to be able to maintain the logic of the smart contract. Because what you can do with introspection is that the script has some consciousness about the context in which it is executed, and then you can verify that in the transaction output, the logic of the script will remain exactly the same. So this is good to maintain the logic of the smart contract verifier. So what is the design? So basically, in this model, you will have a pay to taproot address that will hold the logic and funds. Because if you build like a layer 2 or ZK rollup on top of Bitcoin, what you need basically is a bridge. So you will need the ability to put the funds somewhere. So in this scenario, you will have a taproot address that will hold both the funds of the bridge and the logic of the smart contract that verifies the star proof. And then you will have a pay to witness script hash to hold the state root. So the state root is the representation of the state of your layer 2, basically. And then to move from one state to another state, you will have to provide the star proof to the verifier script. And then the script will verify that the logic will remain the same. This is what I explained, and this is why we need covenant. So you can be able to maintain the logic of the verifier after one transaction. And then it will verify the state transition function. The state transition function is how you move from one state to another state after executing a bunch of arbitrary computation. so transactions or whatever. So in this design, you will the Bitcoin blockchain does not even have to know the kind of virtual machine you are using on your layer 2, but still you will be able to prove the integrity of the computation. Okay, now how we can leverage this for Cashu if we had such a possibility. We could generate Stark proofs for the mint operations. And then we could submit the proofs to the Bitcoin network, to this smart contract verifier. And then what you can do with that, you could have a mechanism where users will be able to send fraud proofs to potentially penalize mints that are cheating. You could implement like some kind of slashing mechanism, something like that. Okay, to do that, you have basically three main approaches to be able to generate the star proofs of the mint operations. The first one, which is the one that came historically, is you need to convert the program, your virtual machine or whatever execution engine you have. You need to convert it to some either custom circuits like that are like some logical gates, or to some airs, which is algebraic intermediate representation, which is a set of polynomial constraints. Anyway, this is just two ways of representing a zero knowledge proof system. So the problem with that it's first, it's very complex. Only few people can actually do that. It's very complex math, and it takes a long time, and also it's error prone. So you will need a bunch of security audits to review the correctness of the representation of the circuits compared to the program. The second approach would be to leverage existing Mint implementations with some ZK VMs. So ZK VM basically is this idea of having a virtual machine that is able to generate zero knowledge proofs of the execution of the VM. So that means concretely that you could reuse some Cashu Mint implementation in Rust or whatever. This is simpler, of course, because you can reuse existing code. But there are two main drawbacks. The first one is the performance overhead, because of course those VMs, those systems, like if you do Rust or whatever, they are not designed in the first place to be ZK friendly. So there are a bunch of operations that are very hard to prove. Just one example, hash functions. As I said, because everything on zero knowledge proof system is modular arithmetic, if you use hash functions like typical hash functions that you know, like SHA-256 and so on, they are using heavily binary operations, which is very hard to prove. So this kind of stuff is painful, and it brings a lot of performance overhead. And the problem with those solutions, there are some existing ZK VMs, but they are not battle tested. They are just in, they are more than proof of concept because they work, but they are not battle tested. And now the third approach that I believe is the best one in this case is the specialized DK DSL, like Cairo. So Cairo is the language, programming language that we created that is specifically designed to be ZK friendly. So everything you implement in Cairo is designed to be able to generate the most efficient zero knowledge proofs that you can. So it's a general purpose language, and it's Turing complete, so you can implement whatever logic you want, and you have the guarantee that you will be able to prove the integrity of computation by generating the most efficient zero knowledge proofs. So it's slightly more complex, of course, because you need to re-implement the logic in a new language. That being said, Cairo is very inspired by Rust, so it's very close to Rust. So for the Rust developers, it's actually pretty easy to build in Cairo, and for the other developers, it's not that hard because it's a high-level language, and it's super efficient. So it's the most efficient zero-knowledge proof scheme that exists, and it's battle tested in production. So, for example, our proving infrastructure is running in production for more than 4 years now, and it has secured over $1 trillion of cumulative volume and processed more than 500 million transactions, which is nearly half of the total number of Bitcoin transactions since Genesis. So this solution is battle tested in production. So what would it look like? So the idea would be to rewrite the Cashu protocol in Cairo to be able to generate stark proofs of the mint operation. So which, as I said, offers a good balance between simplicity and efficiency. And again, a battle-tested and audited language. It's also formally verified. So Cairo is formally verified. So to demonstrate this with a proof of concept, we implemented the blind Diffie-Hellman key exchange, which is the backbone cryptography of Cashu in Cairo. So it works. So you can generate zero-knowledge proofs of the core cryptography of Cashu. So what could we do with that? You could, assuming there will be a possibility to verify the stark proofs on-chain on Bitcoin, you could do forced ecash melting. So the idea would be that users could actually do the melting operation even if the mint is unresponsive. Of course, there are some challenges because in this scenario you would have the mint to put some funds on chain and, for example, keep a part of the reserves for the day-to-day operations and so on. But yeah, assuming the mint will put some of the reserves on chain, then the users will have the ability to force withdraw their funds even if the mint is unresponsive. And then you would have like better mint accountability because you could implement some slashing mechanisms. If any users is able to prove that the mint cheated, then you could actually slash the mint on chain. And then you would have integrity by design, basically, because all the mint operations now are probably correct. You know that the mint actually operated with integrity. Potentially, there could be some interesting changes to do in the way that the state is represented on Cashu and so on. But probably the direction that Kali is designing right now with the proof of liability schemes could be good, like with potentially using sparse Merkle tree and so on. It could be a good direction that could be useful to then integrate Stark proofs. So yeah, to summarize, I believe that Starks can potentially improve Cashu security and reduce trust assumption. And even not assuming OPCAT, even now, you could actually generate some zero-knowledge proofs, as I said, for the proof of liability schemes. And you could submit the proof, like via Noster or whatever, and you could have the users to verify those proofs. So that does not require any soft work. You can use the Stark proofs off-chain, and users can verify the correctness of the mean reports and so on. And yeah, so it will improve the transparency and accountability of the mint operations. So I think there is hope actually for trustless ecash on Bitcoin, and I think it will be perfect because the UX of Cashu is amazing. This is the best payment UX you can have. But if you can reduce the trust assumptions, then I think it can be close to the ultimate payment system. So yeah, hopefully this future will happen. That's it. Is there any question? Yes.
Thank you for the presentation. Let's say you would on chain you prove what is minted. How would that scale with the number of transactions? Is it constant size or?
Yeah, so the proof size is constant, yes. The proof size is always the same. And in terms of scalability, as I said, it's polylog n, basically, the complexity of the verification. So basically, it scales exponentially. So the more computation you prove, the better, actually, because you amortize the cost of each transactions. So in this scenario, you have some trade-offs. So imagine you have the means that will time to time settle on Bitcoin to send the proof. You have some trade-offs because, as I said, it's interesting to batch more computation. So you could have a strategy that is the one that we operate right now for our L2. Either you have sufficient activity and then you submit the proofs, or after a certain period, let's say 6 hours or so, you decide to submit the proof. So you have some trade-offs, but basically, the more you can batch computation, the better. Yeah.
Thank you.
We talked privately earlier, but I just wanted to point out that if the mint custodies some of their funds in a slashing mechanism, the user that proves if there's a bank run, basically users will have to take a haircut unless you operate at like a 50% reserve ratio.
Yeah.
Which is one way that would work, but that's expensive.
Yeah, totally. That will be a challenge. Either you would have like because in this scenario, yeah, it will be a bank run, and probably all users will be wanting to force withdraw. So either you have a mechanism where Mint can actually put some extra liquidity that it puts at stake, and people can slash it. So I don't know why a Mint will do that, but I guess like if Cashu and ecash is successful, there will be a lot of competition for mints, and reputation will be key. So probably the mints that are willing to put some liquidity, some stake at risk, they potentially could be able to attract more users, maybe. I don't know. But yeah, that's a good point. Yeah.
Oh, I realized I misspoke. It would be a 200% reserve
200%,
ratio.
yeah, not 50, yeah. Yeah.
I think in one scenario, when like Bitcoin is not verifying the proofs, there's still like a latency between the time that the operator would be counterfeiting coins and the time that they would actually produce the proof, right? So in theory, like if you really want that to rely on those proofs as like, oh, the funds are good, you kind of like have to like receive the coin and then not actually treat it as like confirmed until the proof gets published, right?
Yeah, totally. There is a latency, and yeah, there is then the notion of finality. What is the finality in this scenario? Yeah, totally. You cannot do like real-time proving. I mean, technically you could, because one cool aspect of zero-knowledge proofs, Stark proofs specifically, because there are two parts. First part is to do the actual execution and then generate the proof. So the second part is asynchronous, but the cool thing is that it's massively parallelizable. Actually, because you can split the generation of the proof, and there is a mechanism called recursion of proof, which is basically this idea to split the computation, to generate small proofs, and then generate a proof of the verification of a proof. This is why it's called recursion, and then it means that you can always catch up with the speed of the execution, which is good. That means that theoretically you can even do real-time proving if you want. The problem is that it will completely defeat the purpose of ecash if you will generate a proof that you will settle on-chain each time. It will completely kill the point of Cashu. Yeah. But you could technically, but there is no point. So yes, there is a question of latency in this scenario, but it's already better than what we have today. Yeah.
Okay, thanks. And one follow-up question. I see someone else has their hand, but we have lots of time. How would you say this compares to shielded CSV? ZK coins, if you're more familiar with that.
Yeah, I haven't looked at the paper yet, but generally the idea of client-side validation, I think it's very interesting in the direction. I think it's actually kind of the next step after ZK rollups, probably. Yeah, I think the main problem is probably the UX, because it gives even more responsibilities to users. Like it's even a step further than self-custody, because you also need to manage properly your state, data, and stuff like that. So I would say the main problem is UX, but I think it's a natural step, and in the future we'll see a lot of that with client-side proving also. Also for ZK, like being able to generate zero-knowledge proofs directly on your mobile phone and stuff like that. So this is the direction that we are taking. This is why we want our prover to be extremely performant even on small devices, and also compatible with WebAssembly to be able to run it in the browser, on phone, everywhere. But yeah.
Keeping track of like the state in the CSV model is not so different than keeping track of your like Cashu nodes, right?
Yeah, maybe. I think it's slightly harder probably, because there is some kind of notion of synchronization, kind of. But yeah, I agree. Maybe it's not that much complex. Yeah.
Something to think about.
Yeah.
Thanks.
more of a comment, but I'm working on a mining use case, and this is directly applicable. So this is fucking awesome. Thank you.
Okay, let's talk about it then. Yeah, cool. Okay, thank you.